Let's talk about graphing transcendental functions. Part 1 of this video will be on graphing exponential functions. Exponential functions, logarithmic functions, and logistics functions are three of the most common transcendental functions. We'll talk about all three as the chapter unfolds, but our focus will be on the exponential and logarithmic functions. This video focuses on graphing exponential functions without calculators. So let's start out with some preliminary work. Exponential and logarithmic functions are inverses. Therefore, when you graph an exponential and a logarithmic on the same coordinate plane, you'll see symmetry with respect to the line y equals x. Let's look at specific pairs of exponentials and logs. If f of x equals 2 to the x, then f inverse of x equals log base 2 of x. If g of x equals 3 to the x, then g inverse of x equals log base 3 of x. So an exponential function and an inverse function are inverses if they have the same base. If I say let's look at h of x equals 10 to the x, then h inverse of x equals log base 10 of x. A lot of times you'll see this written only as log of x. If you do not write the base, it's understood to be 10. And people refer to this as the common log. And of course your calculator is programmed already to evaluate common logs for you. One more that we'll look at on this chart, k of x equals e to the x. K inverse of x is log base e of x. Generally, people don't write log base e of x. Instead, they write ln of x. And I know that this is the natural log. You'll learn to graph all of these as we go in this video and the next one. So when you're graphing exponential functions, they're easy because the domain is all real numbers. Generally, if you pick about 5 x values, and I'm going to let my x's range where I've got a couple of negatives, 0, and a couple of simple positive ones, that'll be plenty to get a good graph. So 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0, of course, is 1. 2 to the first is just 2, and 2 squared is 4. What happens when you plot those points? You're going to get a basic exponential growth function. And remember, I know that if the base of your exponential is larger than 1, it's exponential growth. What happens when the base is less than 1? We'll deal with that one in just a little while. Now, if you were to graph in y sub 1 on your calculator 2 to the x, in y sub 2 e to the x, in y sub 3 3 to the x, in y sub 4 you could graph 4 to the x or 5 to the x, and this could go on and on. I might skip and look at 10 to the x. If you graph any number of those, you'll notice that I have allowed the bases to get larger and larger and larger. Remember, by the way, that e is approximately 2.7. So that's why I put e to the x between 2 to the x and 3 to the x. What you'll see is graphs that look like this. And so they all have the same basic shape. As the base gets larger, the graph gets steeper on the right-hand side, but they all have the same basic shape. That allows me not to spend too much time on these graphs. I just need a few characteristics. So one thing is I'm going to say all exponential growth graphs have the same basic shape that looks like this. Now, your average person couldn't look at that and say, oh, well, that's y equals 2 to the x, or that's y equals 5 to the x. It's okay. As long as you know it's exponential growth, it's enough. It's enough information to work with it throughout calculus. Now, what are some of the features of this graph? Well, number one, I see that it has an y-intercept at 0, 1. Because whether it's 2 to the 0 or 4 to the 0 or 7 to the 0 or e to the 0, you're going to get the answer 1. So 0, 1 is always on the graph. The next thing I notice is that there's a horizontal asymptote over the x-axis or at y equals 0. Something else I note is that the domain is all real numbers. The graph stretches infinitely from left to right without any skips or jumps or holes in the graph or vertical asymptotes. And last but not least, the range of the graph goes from 0 to infinity. All basic exponential growth functions share these exact same 5 characteristics. And then as we tweak the graphs, you'll see some differences in where we might place the intercept and the asymptote. That's yet to come. Now, the domain for this function is still all real numbers, so let me pick a couple of negatives and a couple of positives and 0. Well, 1/2 to the negative 2 means 2 to the positive 2, and that's equal to 4. 1/2 to the negative 1 means 2 to the positive 1. Anything to the 0 power equals 1. Of course, 1/2 to the first is just 1/2. And 1/2 squared equals 1/4. So if you take a minute to plot these 5 points, then your graph is going to be exponential decay. So let me say on your basic exponential function, if your base is less than 1 but still positive, so I probably ought to be more specific and say if your base is between 0 and 1. The bases of true exponential functions are always positive. Then what you're going to get is exponential decay. The other thing I want you to see is that if g of x, if you look at it, g of x equals 1/2 to the x, you could also look at that like it's 2 to the negative x power. And I know that when you have 2 to the negative x, this is telling you that you're going to reflect the original exponential growth graph. You're going to reflect that graph from left to right over the y-axis. So that means exponential growth reflects and looks like exponential decay. So that's another way you can think of this graph. So let's recap what we know about all exponential decay functions. Well, all exponential decay functions have the same basic shape. Whether you have y equals 1/2 to the x, or y equals 0.7 to the x power, or y equals 3/5 to the x power, they all have that same basic shape, even though some will be steeper than others. That means they all have a y-intercept, once again at 0, 1. Anything to the 0 power is 1. They all have a horizontal asymptote, which overlaps the x-axis. They all have a domain of all real numbers, and they all have a range of 0 to infinity. So you see that I'm basically, other than the shape, recording the exact same 5 characteristics. Therefore, Since all of these shapes that fall into the exponential growth or exponential decay category, since they all look very, very similar to one another, I want you to show 3 specific things when you graph these. And when we graph, we're going to graph without a calculator. And as much as possible, we're going to avoid T-charts from now on out. So I need you to start with the right shape. I need you to add the horizontal asymptote to the graph, particularly if you've moved the graph up or down. And I need you to plot one specific point. It's the point that starts as a y-intercept, but after you move the graph up, down, left, or right, it may actually not be an intercept anymore, but that's still the point that I want specifically plotted. So this is something that I've seen people do that might help you. A lot of people start out and say, all right, y equals 5 to the x is your parent function. So I'm going to show you taking a series of baby steps. Is 5 to the x exponential growth or exponential decay? Since the base is greater than 1, it's exponential growth. Now, you need to look at your negatives first. So I would say, well, my first transformation is what's going on with y equals negative 5 to the x? Well, that transformation flips the graph vertically over the x-axis, so the horizontal asymptote doesn't change, but the intercept does. Because what you're doing is you're making your y values negative, so I'm going from 0, 1 to 0, negative 1. Then I can start to look at my translations. So I can handle my left to right translation first. I know x plus 1 moves a graph left 1. Well, that doesn't change your asymptote, but it does change the intercept left 1. And I'm preserving that shape. And then last but not least, I get around the negative 5 to the x plus 1 minus 6. So that takes your graph down 6 units. So 1, 2, 3, 4, 5, 6. The first thing that you want to record as moving down 6 units is the horizontal asymptote. You need that to make sure that the graph is placed well. Then notice that your intercept at negative 1, negative 1 moves down 6 units to negative 1, negative 7, and then you've got the shape. So I don't want any other point. Even though negative 1, negative 7 is no longer an intercept, that's still the one point I want you to plot. And then if I said, okay, well, what's the domain? You'd say all real numbers. What's the range? You would say from negative infinity up to negative 6. Now, I'm going to do the same thing on this next one, but if you don't label each and every stage, that's fine, because the little baby graphs are optional. All I'm really grading is the final big graph, so the little baby graphs are kind of your own scratch work. So I might start out and say the parent on this one is e to the x. That is exponential growth because e is larger than 1. Now, I'm going to kind of drop my labels. The first thing I'm going to look at is e to the negative x because I tend to do flips and spins first. Let me back up here. E to the negative x reflects the graph from left to right over the y-axis. So that's going to look like that. Now, the hardest transformation with these is what's going on with the 4. The 4 is a vertical stretch. It makes it 4 times taller. It multiplies the y coordinate by 4. So the only specific point that you'll show me is 0, 4. It just stretched the intercept 4 units from the asymptote instead of 1 unit. So I quadrupled that vertical stretch between asymptote and intercept. So now the only last transformation I need to do is the plus 2, and the plus 2 makes it go up 2. So the first thing that I need to show that goes up 2 is the horizontal asymptote, because I'm just shoving the whole graph up 2 by pushing on the horizontal asymptote. By lifting it, it lifts everything. Now the intercept is still 4 units above the asymptote, and there's my graph. So again, the baby steps are optional, but I have found that most students, if they'll do little bitty baby steps, even if they're just tiny, that it does tend to help them be accurate on the final graphs. So let's do 3 more, and then you will know how to graph exponential functions. That'll be enough for everything we're doing in class. So consider my parent function is 7/11 to the x power. 7/11 is less than 1. So this starts out as exponential decay, not growth. Now, the first thing I want to do are handle the negatives. Am I reflecting the graph from side to side or from top to bottom? Since this negative comes up front, it's a vertical. So the first thing I need to do is reflect this vertically, turn the graph upside down. Another way to think about it. Now, the next thing I want to do is look at the x minus 4 part of the graph. That moves the graph right 4. So the asymptote doesn't move, but the intercept moves right 4 to 4, 0 or 4, -1, excuse me. The last thing I want to do is take the whole graph up 3. So first and foremost, horizontal asymptote goes up 3. Then my point right here at 4, -1 goes up 3 to 4, +2. And then repeat the shape. That is enough. You don't need to do anything more for me on questions that ask you to graph. Consider your parent function on this one. You've got pi to the x power. Pi is larger than 1. So we're going to start out at exponential growth. Now, let me color code these to help you keep up with where I am in the problem. I'm going to deal with this negative first. It really doesn't matter which one you deal with, but I'm going to color code so you can keep up. The first negative, if it precedes or the whole entire equation, or if it follows right after the equal sign, that's a vertical flip. Flip the graph from top to bottom or reflect the graph over the x-axis, however you want to think about it. The second negative right here is a negative x, which means you're flipping the graph or spinning the graph from left to right, or you can consider it spinning the graph about the y-axis. So that makes the graph look like this. Now, finally, I get around to the final answer, so I've got to deal with that -1, and what's that do to the whole graph? It moves the whole graph down 1. That means first and foremost, the horizontal asymptote moves down 1, and then the intercept, which was at 0, -1, moves down to 0, -2, and then repeat the blue shape, and you've got it. And again, I might ask you questions like, what's the range? And you would say the range is -infinity up to -1 with parentheses. Last but certainly not least, the parent function here is just y equals 10/3 to the x. This is not a hard problem, but I just want to call your attention to this. Lots of students see a fraction and immediately think exponential decay. Just remember to think first. 10/3 is larger than 1. So it doesn't matter that it's a fraction. What matters is that the base is larger than 1, hence exponential growth. The only thing you do to achieve the final answer on this one is just left 2. And if I ask you for range on this one, again, it's going to be from 0 to infinity. Again, I mentioned range here, -infinity to -1. So I may ask you some range questions. We are done with graphing exponential functions.